Let's start by discussing the critical section problem. Imagine a system with n processes labeled as P0, P1, P2, and so on. We may also say Pi, okay? Each process has a specific part of its code called a critical section. So the process may modify shared variables or update a table. Or write to a file, or perform similar tasks. So the key rule in the system is that only one process can execute in its critical section at a time. When one process is inside its critical section, no other processes is allowed to enter their critical section. Okay, so this ensures that no two processes are modifying shared data at the same time, and it prevents conflicts and data inconsistencies, as we saw in the previous example. To solve the critical section problem, we need to design a protocol that enables processes to cooperate. So each process must request a permission. Request a permission to enter its critical section. This request is made in the enter section, okay, of the code, okay? And then following the critical section, there may be an exit section, yeah. And also the remaining code is known as reminder section. Before mentioning solutions to critical section problem, we need to learn that a solution to the critical section problem must meet three requirements. To make sure we have a correct solution to the critical section problem, we need to consider three important things. Okay, the first one is mutual exclusion, progress, and bounded waiting. So it's important to check if a proposed solution meets all these three requirements, because even if just one of them is missing, the solution won't be considered correct. Okay, so in mutual exclusion, if process PI is currently executing in its critical section, and no other process can be executing in their critical sections at the same time. This ensures that shared data is accessed by one process at a time. And we can avoid conflicts. In progress requirements, if no process is currently inside its critical section, and multiple processes may want to enter their critical section, only those processes that are not in their reminder sections can participate in deciding which process goes next, okay? So this selection process cannot be delayed indefinitely. And ensuring that processes eventually get a chance to enter their critical section. So if only one process wants to enter, it should be able to. If two or more want to enter its critical section, one of them should succeed, okay? And the bounded waiting requirement, there is a limit on the number of times other processes can enter their critical sections after a process has requested permission to enter its critical section. Okay, so this limits prevents a process from being indefinitely postponed and ensures fairness among processes. Okay, so limit to prevent access from being indefinitely postponed. Yeah. So many solutions are designed until now. We may start talking about them by their types. Types of solution to the critical section problem can be categorized into different approaches. Okay. So in the first approach, you can see it's software solutions. These are algorithms that can be implemented in software independently without relying on any specific hardware assumptions. They are designed to ensure the correctness of the critical sections. In the hardware solutions, these solutions rely on special machine instructions or hardware mechanisms to address the critical section problem. And the hardware provides a specific features or instructions that help synchronize and manage concurrent access to shared resources. In the operating system solutions, the operating system may offer functions and data structures through system or library calls to assist programmers in managing critical sections. These solutions leverage the services provided by the operating system to synchronize processes or threads effectively. And the last type of the solutions, we see programming language solutions. So some programming languages provide built-in libraries or specifically designed to handle this kind of problems, critical section problems. These language-specific solutions offer convenient and standardized ways to synchronize and manage shared resources within the language itself. So these are the different types of solutions which provide various approaches to tackling the critical section problem, catering to different requirements and environments. So let's start with software solutions for critical section problem. So in the algorithm one, it's one of the solutions that is suggested previously. Okay, and the first algorithm, each processes PI continuously loops and waits until it occurs the turn to enter the critical section. The turn is determined by the value of flag variable associated with the other process, okay? So if flag J is true, PI once waits in the while loop until it becomes false, okay? So let's check the progress requirements of this algorithm. It actually satisfies the progress requirements because if no process is inside its critical section and the both processes simultaneously wants to enter their critical sections, one of them will eventually occur the turn. This ensures that progress is made as processes can take turns and entering their critical section. However, the algorithm does not fulfill the mutual exclusion requirement. It is possible for both processes to simultaneously set their respective flags to true, okay, before either of them enters the critical section. In such a case, both processes would be allowed into their critical section at the same time, which violates mutual exclusion. Additionally, the algorithm actually does not provide bounded waiting because there is no guarantee that a process will be able to enter its critical section within a finite amount of time. If one process continually sets its flag to true, the other process may be indefinitely delayed in entering its critical section, which violates the bounded waiting requirement. So algorithm 1 satisfies the progress requirement, but fails to meet the mutual exclusion and bounded waiting requirements. So let's analyze algorithm 2 and its satisfaction of the requirements. In algorithm 2, each process, PI, sets its own flag, I, to true, which indicates its intention to enter the critical section. It then enters a while loop and waits until the flag J of the other process becomes false before proceeding to the critical section. After executing the critical section, flag I is set to false and allow other process to enter. Okay, so algorithm 2 satisfies the mutual exclusion requirement. If one process is inside its critical section, the other process will be blocked in the while loop until the flag J becomes false. This ensures that only one process can be inside the critical section at a time, and it prevents simultaneous access to shared resources. However, algorithm 2 does not meet the progress requirement. If both processes want to enter the critical section simultaneously, a deadlock situation can occur because both processes set their respective flags to true simultaneously. In such a case, both processes will be stuck in the while loop, waiting for the other process's flag to become false. Eventually, it results in a deadlock situation where neither process can proceed. Regarding the bounded waiting requirement, algorithm 2 does not fulfill it. If a process continuously sets its flag to true, the other process may be indefinitely delayed in entering its critical section. There is no guarantee on the maximum number of times a process can be delayed, violating the bounded waiting requirements. In summary, algorithm 2 satisfies mutual exclusions by ensuring exclusive access to the critical section, but it fails to provide progress and bounded waiting. The potential for deadlock and the absence of a limit on waiting times make it an incorrect solution to the critical section problem. Now let's examine algorithm 3. Yeah. In algorithm 3, there's a shared variable called turn, and that is initially set to 0. Each process PI enters a while loop, where it waits until the turn variable is equal to its own process number, I, before entering their critical section. Okay. Once inside the critical section, the turn variable is set to other processes number, and then process proceed to execute the remainder section and before looping back to wait for its turn again. Okay, so algorithm 3 satisfies the mutual exclusion requirement. Only one process can be inside the critical section at a time because the while loop ensures that a process waits until it is its turn as it indicated by the value of turn before entering. Yeah. So this prevents simultaneous access to the critical section, and it also ensures exclusive access to shared resources. Additionally, algorithm 3 satisfies the bounded waiting. Since the turn variable alternates between the process numbers, it guarantees that a process will eventually be granted access to the critical section. And then there is a limit on the number of times a process can be delayed because the turn variable will eventually be set to the waiting process's number. However, there may be a scenario where one process can indefinitely delay the other process from entering the critical section. For example, if P0 enters the critical section, finishes it, and then sets the turn variable to P1, and P1 can enter the critical section and complete it. However, when P1 tries to re-enter the critical section, it will be blocked because P0 still holds the turn. P0 can potentially be stuck in its reminder section indefinitely and preventing P1 from ever entering the critical section again. This situation leads to starvation where P1 is unable to make progress. In conclusion, algorithm 3 satisfies mutual exclusion and bounded waiting, but fails to provide progress. The potential for indefinite delay in entering the critical section makes it an incorrect solution to the critical section problem. Okay. So lastly, algorithm 4 combines the shared variables and logic from algorithm 1 and algorithm 2 and algorithm 3. Let's analyze how this algorithm satisfies all three requirements and solves the critical section problem for two processes. In this algorithm, each process PI sets its own flag to true, indicating its intention to enter the critical section. It also sets the turn variable to the value of other process's number, j, and then the process can enter a while loop that waits until the flag j is false, and also the turntable is equal to its own process number before proceeding to the critical section. After executing the critical section, flag I is set to false, which allows other processes to enter, and the process moves to the reminder section before looping back to the wait for its turn again. So algorithm 4 satisfies all three requirements: mutual exclusion, progress, and bounded waiting. Okay, so here's how. It ensures that only one process can be inside the critical section at a time. If one process is already inside the critical section, the other processes will be blocked in a while loop until the conditions flag j and turn j is true. Okay. This guarantees exclusive access to the critical section, and it prevents simultaneous access to shared resources. Okay. So it also guarantees progress by ensuring that if no process is currently inside the critical section and multiple processes want to enter, eventually one of those processes will be able to do so. This is achieved by the combination of a flag j and turn variables and the while loop condition. If one process has set its flag to true, indicating its desire to enter, okay, the other process will not be able to enter the critical section until the flag j becomes false and the turn variable equals its own process number. And algorithm 4 also satisfies the bounded waiting requirement, since both the flag j and turn variables are involved in the while loop condition. There is a limit on the number of times a process can be delayed. Once the flag j becomes false and the turn variable matches the process's number, the process will be able to enter the critical section. This ensures a bound on waiting times and prevents indefinite postponement or starvation. In conclusion, algorithm 4 effectively solves the critical section problem for two processes. It satisfies all three requirements: mutual exclusion, progress, and bounded waiting. By combining the shared variables and logic from previous algorithms, algorithm 4 provides a correct solution to the critical section problem for two process scenario.